This podcast is on liquids and solids, and it's related to Chapter 10 in the Zumdahl text. Now, liquids and solids are similar to each other in that they're not gases. You see, liquids and solids are incompressible. Their density doesn't change much with temperature, and the reason for this is that the molecules are quite close together in solids and liquids, whereas they're far apart in gases and there is some empty space. Well, what holds them so close together? Intermolecular forces of attraction. Inside molecules, we have intramolecular forces holding them together. We call them bonds. Intermolecular refers to forces between the molecules, or in some cases the ions. Those forces hold the molecules together in what we call the condensed states. Strong ones are covalent bonding and ionic bonding. There are network covalent solids like diamond, and there are lots of ionic compounds where the bonding is between ions. The weaker ones are the ones you may be familiar with from a previous chemistry course, the dipole-to-dipole forces, London dispersion, or what is called hydrogen bonding. During a phase change, the molecules stay intact as the energy is used, if you're heating it, to overcome those intermolecular forces of attraction. Let's look at dipole-dipole forces. Remember that a dipole is a molecule that has ends that have opposite charges. Well, the dipole-dipole force is that they are held together because of those attractions. Dipole-dipole forces are not very strong, but they're strong enough. And there are lots of polar compounds out there. These play small roles in gases because, indeed, that force of attraction would make something be a liquid. Hydrogen bonding, on the other hand, is an expressly strong dipole-dipole force when hydrogen is attached to fluorine, oxygen, or nitrogen. It's these three because they have a very high electronegativity and they're very small, so they can get close to each other. And you remember the force of attraction increases as the distance between the charged particles decreases. And this clearly affects boiling point. This is a graph you will see over and over again. If you look at the hydrogen compounds of groups 4, 5, 6, and 7, you see that in the case of water, hydrogen fluoride, and ammonia, you have what's called an anomaly where the boiling point is higher than it should be, and that is due to hydrogen bonding. You see, water at the top there is quite special. It has two polar O to H bonds. Each molecule also has two lone pairs of electrons on its oxygen. So each oxygen can interact with two hydrogen atoms, and what you end up with is an especially high melting and boiling point for water because of this hydrogen bonding. Indeed, if you look at this, each water molecule can make up to 4 hydrogen bonds. That's a lot of forces of attraction holding it together. Now, London dispersion forces are the weakest, but nonpolar molecules can actually exert forces on each other. Otherwise, we wouldn't have any solids or liquids. The electrons are not evenly distributed in those molecules every instant in time. We have what we call an instantaneous dipole. That's the way that we explain it. So it means that the more electrons a nonpolar compound has, the more London dispersion forces can exist, and therefore the higher the melting point or boiling point for that particular material. Because if you have a dipole on one molecule, it will induce a dipole in the atom next to it. Have a look at this particular example. We have 2 hydrogen atoms, but at any given moment, you end up with the one on the left going polar, the one on the right is then induced to be polar, and then there's a force of attraction between them. London dispersion forces are weak and short-lived, longer lasting at low temperatures, but eventually you may have enough force to make a liquid if it's strong enough. If you look at the compounds methane, ethane, propane, and butane, they're all gases. When you get to pentane with 5 carbons, it becomes a liquid. So is hexane. As we go up, their boiling points increase. That's because they have more electrons, they're more polarizable, and therefore that bigger molecule would have the higher boiling point. But these London dispersion forces are quite weak. They're called, all of these together, van der Waals forces in some textbooks. London dispersion forces, dipole-dipole interactions, and hydrogen bonding. And you just need to remember, and you have this probably from a previous chemistry course, the order of increasing strength. The real bonds are the really strong ones. Liquids. Many of the properties of liquids are due to the internal attractions of the atoms. Things like beating, surface tension, and what we call capillary action. Another one you may not have heard of is viscosity. Viscosity is how thick it is. Stronger intermolecular forces cause these to increase. So let's look at surface tension. The molecules in the middle are all attracted in all directions, whereas the molecules on top are only pulled to the inside, and this gives a surface tension to liquid. Stronger the forces of attraction, the greater the surface tension, and that's especially true of water. Because what we're trying to do here is minimize the surface area. Capillary action is where liquids spontaneously rise in a narrow tube. Intermolecular forces are cohesive, meaning they connect things. Well, adhesive forces always connect to something else. Glass happens to be polar, and so is water. And so what you end up with is if you have a glass tube and some water, the adhesive forces are attracting the water molecules, and lo and behold, you'll find that the water will rise in the tube. And that's because of the similar forces of attraction between the glass and the water. Beating. If a polar substance is placed on a nonpolar surface, there are cohesive but no adhesive forces between the surface and the water. And so here we have a look at a water molecule beaded up on a nicely waxed surface like a car. Viscosity. How much a liquid resists flowing. Large forces, more viscous. Large molecules can get all tangled up. For example, cyclohexane has a lower viscosity than normal hexane. That's because the cyclohexane is a ring structure. It's more compact, and there is less chance for the intermolecular forces of attraction to have any effect. Well, how much of these? The stronger the force, the bigger the effect. Hydrogen bonding, followed by dipole to dipole, followed by London dispersion forces. You may feel we've gone over and over this over again. It's for a reason. Let's look at a model of a liquid. You can't see the molecules, so we picture them as being in motion but attracted to each other with regions where they're arranged like solids, but they're much more disordered. There are fewer holes in a gas. It's a highly dynamic situation. Phase. The phase of a substance is determined by three things: the temperature, the pressure, and the strength of the intermolecular forces of attraction. And this, too, is something that you need to be very familiar with. Solids. Solids come in two major types: amorphous and crystalline. The amorphous are those which much disorder in their structure, whereas crystalline are quite regular. Crystals are lattices. That is a three-dimensional grid that describes the location of the pieces in the crystalline solid. The cell is the smallest repeating unit of a particular lattice, and there are three common types. The first one is the classic cubic unit cell. Another one is called body-centered cubic. And all of these drawings are in your textbook. And finally, you have face-centered cubic. Well, speaking of the book, yes, it goes on and on about the solids and using diffraction patterns, and talks about metals and the closest packing model. That's all pretty interesting, but in general is not on the AP exam, and indeed isn't much that what regular chemists spend time on. We need to focus on metallic bondings, and in the next podcast we'll look at the question of why do metal atoms stay together, and how does their bonding affect their properties. There are many amorphous solids. Glass, but we tend to focus on crystallines. The two types are ionic solids that have ions at the lattice points, and molecular solids have molecules. example that's best is sugar versus salt. Sugar makes crystals, salt makes crystals. The only difference